Welcome everyone, happy Friday. We are going to do a quick recap of what happened last lecture and then pick up where we left off, which was investigating the kind of strange behavior that the magnitude plot of a second order quadratic pole exhibits. So let's switch over to the other screen. And Ernie's question was, what is up with this versus that? And what is up is they both represent the natural frequency of their respective quantity. But if I were to have on the top omega n sub 1, I'd want that to be a different frequency than if I had on the bottom omega n sub 1. So this is just, if I write that as omega 0 sub 1, then it's still a natural frequency, but no one will confuse it with omega 0 sub 1 on the top and omega n sub 1 on the bottom. More subtle is that I wrote the Greek letter xi here and the Greek letter zeta here. They look similar enough that I figured I could sneak it by. So the reason that I used a different subscript is because I wanted to let the natural frequencies on the top be different than the natural frequencies on the bottom, possibly. Does that make sense?
Yeah, that makes sense.
Cool. Okay, so we can think about all of our LTI transfer functions as being composed of these 8 ingredients. It can have possibly more than one of the ingredients, but it can't have anything that's not here. If it's got real poles, then it's got real poles. If it's got complex conjugate poles, they will appear in quadratic pairs. And the same for zeros. So what we did was we ran through the Bode plots for each of these ingredients. So we did the constant, we did the 0 at the origin, we did the pole at the origin, we did the 0 not at the origin, we did the pole not at the origin, and all of those pairs were flip-flops of each other. So if you know one, you can do the other. And the first beast that was different was the quadratic pole. And so I want to take a little bit of time here to remind you what's going on. So it started off kind of similar. It started off with, at low frequencies, the magnitude looks like 0 dBs. So that's how we got this point, this asymptote. And at high frequencies, the PowerPoint crashed last time, but at high frequencies, so omega much, much bigger than omega n, we got something like the equation H6 in dBs was minus 40 log omega plus 40 log omega n. And so this is of the form y equals m x plus b. And so that's how we got this linear shape asymptote down here. So with a slope of minus 40 decibels every decade, with an intercept at omega equals omega n. So this is the x-intercept, if you like. So what happened was when we started to do the third case, the middle case, the omega equals omega n, things were different. Before, we just got a nice number. It was always root 2 or 1 over root 2, and it was a fixed number. But here, the magnitude depends on zeta, and zeta is independent of omega n, so you can have quadratic poles with the same omega n but different zetas, and they will have different Bode plots. That's what we just saw. So they will all start at flat 0 dBs. They will all end up sloping down at minus 40 dBs per decade, but they will behave differently in and around this region. Okay, so today we're going to take a good hard look at that. And we kind of got a rough idea of what's going on by analyzing when does 2 zeta become greater than 1, less than 1, or equal to 1. And those three cases were here. That's when this logarithmic term, this dB term becomes either positive, 0, or negative based on if zeta is bigger or smaller than 1/2. Okay, so I think the most natural first question to ask is, when exactly will there be resonance? And so resonance is this phenomenon of a rise before the fall. So both of these two curves have it. What is that, like burgundy and peach? They both resonate, i.e. their magnitude responses rise before they fall, but orange doesn't. Orange just kind of sags, just like a regular real pole did. And so I think the first question is, when does it happen and when doesn't it happen? Where it is this phenomenon of resonant peaking. So now we get into the new stuff. Questions on that review? Okay, now we get into the new stuff.
I only
So
cared about the flat approximation. Which part of that equation would you just focus on for like the second straight line?
I'm sorry, can you ask the question again?
If you're not worried about what's happening at the middle with the going up or going, you know, would which part of the equation in the denominator is causing it to slope down like that?
This one.
Okay, so you don't have to worry about that right part at all with the.
So if you let omega get very, very large relative to omega n, then omega squared is going to be much, much bigger than omega.
Okay.
Does that make sense?
Mm-hmm.
And if I divide through by omega n squared, it's the same story. So
Okay.
yeah, if we're looking at magnitudes, this one will dominate for very high frequencies. It will even dominate this one. And this squared is where you get the 40 instead of the 20 dBs.
Thank you.
Okay, so let's take a look at the magnitude response kind of formally here. So again, when we're looking at the decibel value of the magnitudes, we're taking the 20 log. So I guess I actually skipped a step already here. H6 in magnitude is going to be the magnitude of 1 over 1 minus omega over omega n squared plus j 2 zeta omega over omega n. And so this negative comes from the 1 over, right? So I got rid of the 1 over and I factored out the negative out there. And logs let me do that. Okay, so these bars are just standard complex magnitude, which means we should be able to use the Pythagorean theorem to find the magnitude of this thing. The real part is this, and the imaginary part is this. Therefore, if I square the real part and I add it to the square of the imaginary part, take the square root, I've got Pythagoras's favorite theorem. What else can we do here? We can take the power of 1/2 and change the 20 to a 10. And we get this expression. And I want you to notice that this is technically, it's a function of omega, but omega always travels with omega n. So if we just do a variable substitution, then we can simplify our lives by just discussing what this function does as a function of x. Okay, so I'm just doing a variable sub to get rid of the fractions here. But if I do that, then this fraction becomes x squared, this fraction becomes x, and I'm squaring the whole thing. So the reason that I called this f of x and I'm dropping the log is because I'm going to try to maximize f of x with respect to x. Right? I'm looking for a peak here. So we're going to use some calculus 1 on this. We're going to take the derivative and set it equal to 0 and look for where it peaks. But the idea is I don't have to analyze the outer log part because, and I don't know if this is a common knowledge at this point, but if you maximize a function of a function and the outer function is always rising or even always falling, then it suffices to optimize the inner function, because the optimal points of the inner function will be the optimal points of the outer function. So what did I just say? I'm trying to maximize g of f of x with respect to x, where g is negative 10 log of x. Okay, so this function, negative 10 log of x, is monotonically, what do you think, increasing or decreasing? Okay,
Decreasing?
exactly.
It looks parabolic.
Mhm.
Well, so the log function, if I just plotted log of x, it would look something like that, yeah? So if I plotted negative log of x, or negative 10 log of x, it would look something like that. So g is what we call monotonically decreasing. So that means that if I'm trying to optimize g, then, and g is a function of another function, then all I have to do is optimize f, the inner function, and the optimal points of f will be the optimal points of g. Okay, we could get maximums turning into minimums, but that's okay if all we're looking for are extrema, if that makes sense. I'm not going to go into that proof, the fact that you can just look for the optimal of the inner function with respect to the outer function, but I want it to kind of make sense. If I have a ranking of things, like say, I don't know, my favorite sports teams. So like the Dodgers would be down here, the Giants would be up there, the Padres, well, the Padres don't really count. The A's would probably be there. So you can think of this as a ranking. And so the maximum of all that would be this point, the Giants. And therefore, if I take a function and I were to, at least as long as the function is monotonic, right? If it's, say it's linear, then it's going to take this point and map it to a point like that. It's going to take this point and map it to a point like that. It's going to take this point and map it to a point like that. That's what a linear function does. So therefore, the largest point that we started with gives me the largest point that we ended with. Okay, that's the idea. And it didn't have to be linear. All it had to be was increasing. So as long as you start with something that's well ordered, you'll end up with something that's well ordered. And it doesn't have to be sports teams either, clearly. There's a question in the chat on slide 14. Every time we use that formula, we always do plus minus 40 dB. Can you, I don't understand. Every time we use that formula, we do plus minus 40 dB. I don't, I guess, do we need to redo this derivation? Okay, I'm gonna go backwards, people, sorry. For omega's much, much bigger than omega n, she says she's got it, never mind. Well, I've already started, so too bad. We get magnitude of H6 in dBs is minus 20 log of negative omega over omega n, inner squared, outer squared. Okay, because like I said, this one goes away, and we are looking at the Pythagorean theorem here. So we're square rooting the squares of the legs. This square root and that square goes away. So we end up with minus 20 log of omega over omega n squared. The 2 comes out because we're taking a log, so we get minus 40 log of a quotient. And log of a quotient is difference of logs. Minus 40 log the top, minus 40 log the bottom. Okay, so that's where the 40 dBs per decade slope comes from. Great. Yeah, another way to remember this is that every pole gives you 20 dBs of drop. And a quadratic pole, a pair of poles, a complex pair of poles, it's 2 poles. So you should get 40 dB drop. And the same for zeros. Every 0 gets you 20 dB of rise. Okay, good. I'm glad I cleared that up. So, right, back to optimization theory. We are looking to maximize or optimize this function because it will tell us about the optimal points of that function. So we're going to take this derivative. Well, I already took the derivative for you, and you get this expression. We are then going to set this equal to 0, and we're going to try and solve it. Well, clearly there's one solution, x equals 0, or the other stuff equals 0. Okay, so let's solve this, and we'll talk about the 2 solutions here. This is the same as x squared equals 1 minus 2 zeta squared, so x would be plus or minus root 1 minus 2 zeta squared. Okay, so it looks like we have 3 possible solutions here. Tell me, is this one valid? Is it interesting? I guess those are 2 different questions. Is this a valid optimal point, or what we call extremal point?
Is for a log plot there is no 0? Is that the point?
That is the point. Well, x equals 0 corresponds with omega equals 0, which is way the hell out there. And what it tells us is that the graph is flat at DC. That's what that result says. So this is flat at DC. But we're not interested in DC, we're interested in the resonant peak. So while it's true, it's not interesting. At least it's not interesting to our objective today. So this is the more relevant one. This says that and we're not going to look at the positive, or the negative root, because again, we're looking at only positive frequencies because we're looking at Bode plots. But it is technically true that if you were to do this over both positive and negative frequencies, you would get symmetric extremal. So this says that there is an extreme point when omega equals omega n times the square root of 1 minus 2 zeta squared. And I'm going to give this omega a special name. I'm going to give this the name omega sub r, because this is the resonant frequency. This is the frequency where the magnitude plot peaks. So the astute viewer will see that this also depends on zeta. Everything comes down to zeta here. It also depends on omega n, but that's kind of a boring relationship. Yeah, if omega n goes up or down, the resonant frequency will go up or down. But the zeta is what I want to focus on, because this radical has a negative under it, which should raise some I don't know, red flags, maybe orange flags, because we need real frequencies. But if zeta gets too large, we're going to end up with imaginary numbers here. And so what's the limit on zeta? So we need 1 minus 2 zeta squared to be positive. Okay, well, I think we can rearrange this. This is 1 bigger than 2 zeta squared, 1 over 2 bigger than zeta squared. So zeta has to be less than 1 over root 2. And for those of you keeping track at home with decimals, this is about 0.707. So again, this is a zeta value. This is not a dB value. I know that we get a lot of root 2s when we talk about dBs as well, but this is disconnected from that. So this tells me that we will only get resonant behavior only when zeta is smaller than 0.707. Okay, this is important because what it means is that not all complex conjugate poles will behave the same way. Those that are only lightly underdamped, i.e. those that have a large zeta close to 1, will sag. They won't rise and then fall. They will just droop. Zetas that are more heavily underdamped, i.e. those with zetas of 0.6, 0.5, 0.4, 0.3 at that direction, they will exhibit resonance. They will rise before they fall. Okay, and so we didn't have this kind of delineation for the real poles or the real zeros. This meant that there are now 2 classes of complex conjugate poles. There are lightly underdamped, and there are more heavily underdamped. These guys, these will just droop or sag. These ones will resonate. Is that, are there questions on that?
I think we've mentioned it before, but when you wrote the expression for the resonant frequency, and you multiplied it by Wn, is this the assumption that Wn is just 1? Because
no, so x we defined as the ratio of omega to omega n.
Got it. That's
so all I'm doing is moving the omega n over.
Okay. Thank you.
Yeah, sure. But that actually brings up a good point, and I'm glad you did it, because this fraction, this root, as long as zeta is less than 0.707, this radical is always less than 1, which means that when the resonant frequency is defined, the resonant frequency is always less than the natural frequency. Less than, I guess, or no, less than. Connor, what's up?
When you say droop or sag, you're talking about the resonance, right? Those curves on the last page?
Yeah, so this is what I'm calling droop. And these two are both resonating.
Okay.
For real poles, all they did was droop. All you get with a real pole is meh. Well, they don't make that sound, but you get the idea. The interesting thing with quadratic poles is that they can simply sag, or they can do other stuff. Okay, and so this result was showing when they do which, and it depends on zeta. Okay, so now I think the question is, now that we know which complex conjugate pairs will resonate, I think the next logical question is, how high is the peak? How much do they resonate? What's the most gain we can get out of these things if we so desire? Or what's the worst case gain if we really don't want things to amplify? So 2 sides of the same coin there. So the height of the resonant peak is simply plugging in the resonant frequency into our expression for the magnitude. Okay, so now I took all the omegas in the former slide and I replaced them with omega r's, resonant omegas. Okay, so using the expression from the last slide, everything inside the square brackets here reduces to this, 4 zeta squared minus 4 zeta to the 4. This is the difference of squares, so I actually pulled the power square out, and I took, 2 for here, I took a square out, but I put the negative in, just because I want to write this eventually as a decibel value. So I want a 20 log, not a minus 10 log. Okay, so the height of the resonant peak is exactly this. And so take a quick gander at that and tell me, as zeta gets very small, as zeta goes to 0, does this get large or small, negative or positive?
I think as it gets pretty large, it would be more certain that it's positive.
As what gets large, sorry?
Zeta?
So can you flip that around when zeta gets small?
Oh, yeah. My bad.
The magnitude gets large.
Right, so when zeta gets small, this term looks like 1, and this term looks like small. And so I get 1 over small, and so everything inside here looks like big, and dBs turn big things into big things. So like logs are themselves monotonically increasing. So if I take something big and I take the log of it, it's still, I mean, it's not as big as it was, but it's still big. So the idea is that as zeta gets smaller, the resonant peak gets taller. That's the relationship I wanted you to see here. In fact, you will see both of these formulas in your textbook. There is a common shorthand for this that says, you know what, when zeta is really small, this term doesn't matter at all. And so let's just write it like this. And that's, I mean, that's fine. It's not as accurate as the top one. I guess I don't need to like cross out my own notes. It's probably confusing for you. I just want you to I want to make sure that you know which of the things on the slide I'm talking about. I think that's my motivation. This is a common approximation, but it is only a valid approximation for very small zetas. For zetas between like 0.5 and 0.7, don't use the approximation. You've got to use this one, or else you'll get nonsense. Okay, any questions on that?
Could we just always use that square root equation?
If you've got a calculator, yes.
Okay.
Yeah, for sure. But if you are trying to do something quick and dirty, then the bottom one could give you an approximation, and it's easier to do in your head.
Okay, thank you.
Sure thing. Okay, so that whole analysis is the reason, or the derivation behind these kinds of pictures that you'll see in your textbook or on anything having to do with complex conjugate magnitudes. So this is a little strange. This is on the horizontal axis. It's not omega, it's x. It's the ratio of omega to omega n, which is why all of these peaks kind of line up right here. So remember that we're going to do x resonant, which is, remember, omega r over omega n, was the square root of 1 minus 2 zeta squared. And the resonant peak, so peak height, is 1 over 2 zeta, I forgot the equation, 1 minus zeta squared.
Is that the same as like a normalized frequency?
That's exactly what it is. Yeah. Frequency ratio or
Yeah.
normalized frequency. Yeah, this is a common way to say, like, this will be what happens relative to the natural frequency. Exactly. And so there are a couple things here. When zeta gets small, we see the peak gets tall. Cool. When zeta gets large, right? So now we're talking about the in between maybe the 0.6 and the 0.8. The 0.6 has a peak, but it's very small. The 0.8 has no peak. It just sags. Okay, so if you didn't believe me, maybe this, I don't know, textbook generated image will convince you that between 0.6 and 0.8 is the dividing line between what peaks and what sags. However, for zetas very close to 0.7 but smaller, the peak is very small. And also what I'd like you to see is that this is not a trick of the eye, is that the peak location is actually going to lower and lower frequencies. So this is kind of, I've tried to connect the tops of all of these curves. And that's because of this term. As zeta gets bigger, this fraction gets smaller. And so the peak height occurs earlier and earlier relative to the natural frequency. Okay, so there's two things going on here. As zeta gets small, the peak is moving closer and closer to omega n, and the peak is getting taller and taller. Okay, so it's marching left to right and also growing from near zero to near infinity. Can you hold those two things in your minds? This is complicated stuff, I think. Any questions I should ask? All right, so let's talk about phase, because we've kind of neglected phase so far. So this, I'm not going to do a whole big derivation on it, but you get actually a similar kind of behavior that the phase transition of a quadratic pole depends on zeta. Some things don't depend on zeta. So let me point that out. Is that 1 decade below, all of these curves, they're all approaching 0 degrees, one at omega equals omega n over 10. So 1 decade below, they're all going to 0. 1 decade above, they're all going to negative 180 degrees. Okay, so this is another like kind of rule of thumb. Every pole drops you by 90 degrees. A complex conjugate pair of poles is 2 poles, so there should be 180 degrees of drop, phase drop. All of these curves pass through negative 90 degrees at omega n. Okay, so there's no resonant shift here. Everything passes through omega n at negative 90 degrees. That's a super helpful point if you're trying to sketch these out. The difference comes in how these curves get from 0 to minus 180. The smaller zeta becomes, the longer they stay high and the steeper the waterfall is. The closer to 1 the zeta becomes, the more like it's just 2 real poles. And I think that's a super helpful way to look at it. Because what happens if zeta equals 1? Well, that means that this is equivalent to 1 over s plus p repeated. And this is just 2 real poles. So this should have, each one should have a minus 45 degree per decade drop, but there are 2 of them. So therefore, in total, they should have a minus 90 degree per decade drop, which is exactly what you would sketch. You would go from here down at minus 90 to there. And so you see that that approximation is the closest to the zeta equals 1 curve. And as any zeta that's smaller than 1, it's going to end up pushing the waterfall to be steeper and steeper and steeper. Okay. This is akin to what you probably learned as the quality factor back in 212, this Q factor. It's the same idea. Questions on this? All right. Let's do, yeah, we got one more, then we'll do an example. So the last ingredient is a pure delay. So what does the magnitude of this function look like? So let's get a smaller pen here. Magnitude of h8 of omega in dBs is 20 log the magnitude of e to the minus j omega capital T. But this is magnitude 1. Okay, so regardless of omega, this is 20 log of 0. Sorry. This is 20 log of 1, which is 0. That's what I was getting at. So just like a positive constant had 0 phase, a pure delay has 0 gain and 0 attenuation, if you like. How about the phase? So the phase of e to the minus j omega t is simply minus omega t. So this is a linear phase drop. So if we're going to plot this versus so as omega gets bigger, this becomes more and more negative, and so we're looking at this would be linear if we plotted it on a linear scale. So let's just plot it on versus the omega scale. This would be if we say that here's 0 radians per second, then this is a simple straight line. I know I'm plotting it on log paper, but the idea here is that this is just the line with its slope negative capital T. Okay. If you were to then take the log of the horizontal axis, that would have the effect of squishing the horizontal axis, so you would get something nonlinear. But the idea is that this will take your phase of H8, and linearly drop it over time. Or sorry, over frequency. Okay, so let's talk about an example. I added this to the slides after the fact, so I'll give you a second to copy down this example, but I think we are running low on time, so I think I'm just going to take over in a second. So the challenge for us is to sketch the Bode plot. So I'm going to do magnitude on this one, so magnitude of g omega, and I'm going to do phase on the next slide. Okay, so the whole point of all of this was I don't have to look at this monster and do it all at once. I'm going to do them piece by piece. Okay, so let's first kind of label the important parts here. So where are the relevant frequencies? We've got something at 10 radians per second. We've got something at 2 radians per second. We've got something at 50 radians per second. And so I think if we do something like 0.1, 1, 10, and 100, that should give us a good range. So this is the log omega axis. Okay, so let's do them piece by piece. We'll do the piecewise guys in green. So first off, the first ingredient is the constant. So let's put 0 dB line right here. The constant of 5 is, what's 5 in decibels? That's a good question. If only there were a calculator. Okay, about 14 dBs. So a factor of 5 will count as 14 dBs. So here's 0, 10, 20, which means that this is our constant. So I'm just drawing them all individually, and that way I can then graphically add them up at the end. The next one I want to do, so I got that one, the integrator. So remember the integrator passes through this point right here, 1 radian per second, comma 0 dBs, and it has a slope of minus 20. So the integrator looks like this. This is actually easier than doing it on a chalkboard. And I want to take a moment here and remind you that the integrator never kinks. The integrator is always falling. And so I see a lot of people do something like that for their integrators, and that's a bad idea, because that's a pole at 1. That's s plus 1. We just have s. And so the other thing that I see is that when people get to the top of the diagram, then they flatten it out. And that's also, like, that's even worse. That's just, you ran out of graph paper and then it somehow changes the behavior of an integrator. That's not true. So this arrowhead continues north and west. This arrowhead continues south and east. Okay, so let's do, what do you like, the 0 next? 0 is going to be kind of easy. So the 0 hangs out at 0 dBs. And if we're just doing the straight line approximation, then at 10 radians per second, it takes off upwards at 20 dBs per decade. So this was the integrator. This was the real 0. And let's do the real pole. So the real pole sits at 2 radians per second, which means that it's going to be flat. And then when we get to 2, which is the first tick mark after 1, he said, because log paper is hard to interpret, this then falls at a parallel slope to the integrator. So this is the real pole. Okay, so last thing is the complex conjugate pole. Before I do that, because it's going to get a little hectic, questions on the 4 ingredients that we've drawn so far?
I see the P and the I, and there's no, correct, that there's a P and an I in this transfer function?
I see only S's.
Well, I'm trying to relate this to
sorry,
what we did
you dropped out there a
yesterday
bit.
and trying to make sense of it in my head, because you were mentioning something about, I'll private message.
Okay. So yeah, I mean, this is something we could have done in 228. There's nothing control-y about this example. It's just an arbitrary transfer function that has lots of things that I want you to be able to do. So I wouldn't read too much into trying to make this a controller. What's the controller? What's the plan? Is this closed loop? Is this open loop? Just go with it. But yeah, if I started talking to you about frequencies in lab because of the low pass filter and the differentiator, we will get to that. That will clearly become evident here. Okay, so the complex conjugate pole, pair of poles, has a natural frequency of 50 radians per second and a zeta of 0.3. Because I'm looking at this term, so this I read as 2 zeta j omega over omega n. So the omega n is 50 and the 2 zeta is 0.6. Okay, so if I'm looking, and this zeta is quite small, so I'm actually going to use the approximation. So this is going to mean it's, well, I mean, we got MATLAB up. Why don't we just do it? So omega n is 50 and zeta is 0.3. So omega resonant is omega n times square root of 1 minus zeta squared. Okay, so 47.7 radians per second. And the peak height, so peak is going to be the dB value of 1 divided by 2 divided by zeta divided by square root of 1 minus zeta squared. Did I flub this? I think I got the wrong expression for the resonant peak.
Isn't it 1 minus 2 zeta
Yeah,
squared?
yeah. Omega n times square root of 1 minus 2. There you go. Okay, we would have been off by 2 radians per second. That's what's nice about log plots, is it takes those errors and it just kind of squashes them away. So we're going to expect a peak of about 5 dBs, and the peak height has to occur at 45 radians per second. So omega r is 45 and a peak of 5 dBs. Okay, so let's see what's going on here. So if this is 20, 30, 40, this is 50, which means a 5 dB peak is going to occur there, and it's going to be just before 50 radians per second. So we're going to see something like this. And now what I'm going to do is I'm going to do a 40 dB per decade asymptote emanating from 50 radians per second. So I'm going to go down 1, 2, 3, 4, 40 dBs, and I'm going to go over to 500. So here's 200, 300, 400, 500. And so this is my asymptote, which I'm going to draw dashed. And because that's going to help me sketch how this curve approaches. Okay. So did you catch that? Like, I wanted to show you the mechanics. I drew the 40 dB per decade asymptote rooted at the natural frequency, and then I used that to help me approximate how this actual curve will sag onto it. Okay, so this is the complex conjugate poles. Okay, so we've got the 5 ingredients individually, and now it's time to put them all together. So I like to do this starting at low frequencies and working my way up. That's because at low frequencies, you've usually got the fewest number of things that are active. And what do I mean by active? I mean, look at these 3. The real zero, the real pole, and the complex conjugate poles. They are all doing diddly squat at low frequencies. They're all 0 dBs, which means that I only have to add the 2 active things. That means the integrator and the constant. So if I take a slopey line and I add a constant to it, it's still got the same slope. It's just moved up by that amount. And so at low frequencies, I'm going to have a parallel line that goes up forever that way. And then it keeps going until the first thing activates. So this was integrator and constant, and right about here, we start to feel the effect of the real pole. So this now, I have to double the slope. So I went from -20 to -40, which means if I go from this point, I go 1, 2, 3, 4 down, and 1 decade over. So I'm heading for that point. And I keep going until I feel the effect of the 0. So the 0 says, okay, I've got -20, -20, +20, which means the slope at about 10 radians per second is only -20. So luckily, I'm already at this line that I have drawn. And so I get to follow that line until I get to where the resonant peak starts to take over. So now I'm adding a skosh of resonance, but I'm adding a hill to something that's already sloping down. So the net effect is that the hill kind of gets tilted and pushed on its side a little bit until eventually the floor falls out and we're falling down here at -60 dBs per decade. So this is my rough interpretation of what the overall magnitude of this plot, of this transfer function will look like. And if you like, you can convince someone who's reading this that you know what you're doing. You can say this is a -20 area, this is a -40 area, this was a -20 area, and then this was a -60 area. It's common to, like, especially if your pen is as if your penmanship is as poor as mine, it's nice to tell the reader what the slopes are when you can. Okay, we're gonna have to do the phase on Wednesday. Enjoy your long weekend at home.